Welcome to Lecture 29 on partial differential equations. During this lecture, we'll be exploring solutions to the KdV equation. In particular, we'll be looking at special solutions such as traveling waves and self-similar solutions in the first part of the lecture. During the second part, we'll be giving an overview, or in fact more like a brief sketch, of a general method of solving the KdV equation with the inverse scattering method. And we'll look at specific properties of 2-soliton, 3-soliton, and dispersive wave solutions. During the previous lecture, we illustrated how the potentiality existed for the dispersion, which tends to flatten a wave and decrease its amplitude, could counteract the nonlinear velocity that tends to cause a shock wave in a solution, and that these two effects could balance each other out to make soliton-like solutions that are basically traveling waves through the medium. During this lecture, we'll make that thing concrete and find the expression for those solutions in detail. So what we're going to do during this lecture is basically seek traveling wave solutions to this nonlinear equation. And the way we do it is simply to assume that we have a traveling wave solution. In other words, that the solution now is not a function of two variables, but rather a function of one variable, which then serves to basically vect a fixed profile along the x direction. In other words, xc is simply a variable that's associated with the characteristic variables that we found for linear problems, and that c is simply equals to x minus ct, where c is a constant that sort of depicts the velocity with which this profile is traveling in the x direction. And while there is no guarantee that this ansatz will give a solution, what we do is we assume it, work out its consequences, and then find that there is in fact a class of solutions that solves this fully nonlinear equation that has this form. So the first step in doing that is simply to work out the derivatives, namely each thing that enters into the KdV equation. And the way we do that is simply to observe that u of t now becomes the derivative of f with respect to xc multiplied the derivative of xc with respect to t. So that's minus cf prime. The derivative of u of x, the derivative of u with respect to x is simply f prime, so df dxc, and the triple derivative is just f triple prime. We substitute this into the KdV equation to yield something that I call the restricted KdV equation, basically restricted to the assumption that you have a traveling wave solution. That is something of this form. And this equation we can integrate at least once to start with by observing that this linear term is basically the 3 times or minus 3 times the derivative of f squared. Okay, so f squared's derivative is basically 2f prime. Okay, so we integrate once, we get that minus cf minus 3f squared plus f double prime is equals to a, where a is the integration constant. To proceed further, we can use a trick that I may have mentioned before, but that I'll review again in detail here just for purposes of clarity. And this method you can apply whenever the differential equation does not have an explicit dependence on the independent variable, in this case c. Okay, so what we're going to do is we're going to say let p equals df dxc, and then work out the equation for dp df. Okay, so we have that dp df is equals to dp dxc multiplied by dxc df, which is just 1 over df dxc, which is just then p again. So we have that dp dxc is simply f double prime over p. And we can then use this expression for f to substitute in for f double prime. So we're now going to have f double prime is equals to p times dp df, and we substitute it in there. And then we're left with this equation, which allows us to basically use the fact that basically separate the equation out, and we move the f to that side, and then we integrate it, which basically gets a half p squared from this term is equals to af plus c over 2 f squared plus f to the 3 plus the integration constant b. And we can now, recalling that p is just df dxc, we can integrate it one more time, but before, and you can in fact do it, but the equation or the result is complicated. It's easier if before we do that we impose boundary conditions on the nature of the traveling waves. And the boundary conditions we're going to impose is basically that they go to 0 at infinity in the wave's amplitude, first and second derivative. So the assumption is basically that the traveling wave is localized away from infinity. Okay, in other words, you have a solitary wave. Okay, and those boundary conditions, if you make them explicit, is simply that f prime and f double prime go to 0 as c goes to plus minus infinity. And if we make that assumption, we substitute that back into the equations we have from this one that f goes to 0 and f double prime goes to 0, thus a is equals to 0 because it's a constant. And if you then substitute that into this equation, you have that p, which is f prime, goes to 0, a is already 0, f goes to 0, thus b is equals to 0. So that solitary wave boundary condition basically implies that a equals to b equals to 0, which simplifies the thing we have to integrate to the following equation. Okay, we then take the square root of the right of both sides, and we're left with solving the following integral, which is basically df divided by the square root here on the right hand side is equals to plus minus the integral over dxc. And we can integrate it. And the way we integrate it is to make the following substitution. Generally, if you have a square root of a function, you use trigonometric or hypertrigonometric functions. And if you have a plus, it's usually cosh or sec. And so let f be equals to sec squared, and the reason is we want to get rid of the square root. And if we make this assumption and we work out the consequences, we basically have to work out what df is to replace that, and we're also going to work out what the square root is, and to do that we simply need the identity that this is equals to minus c over 2 1 minus tan squared, and that will make a square in the square root. And we have that df is equals to minus c 2 times sec times the derivative of sec of theta, which is just sec tan d theta. Okay, so we substitute that above the line. Here we basically have that we have tan square root of it, so we have tan which cancels with the tan and the df. We have f here, which is sec squared, which cancels here with a sec squared, and what we are left with is the integral from minus 2 over square root c d theta is equals to plus minus the integral over dxc, or theta is equals to plus minus the square root of c over 2 c minus x0, where x0 is an integrating constant which we have just chosen so it can set the initial position of the profile. And then we also have to observe from the solution that we're going to have to assume c is greater than 0 in order to get a solution. And another observation is the substitution we've made here, namely that f is equal to sec squared of theta, is an even function of theta. In other words, if we replace theta with minus theta, it makes no difference. So we can ignore this plus minus, and we can thus write down the general traveling wave solution in the following way. Okay. So, and it's important to note that this traveling wave solution is no longer a free profile set by the initial conditions as we had in the normal advection equation, but a very, very specific profile. Only these profiles will actually travel without changing. Okay. And there are a lot of features about just this individual traveling wave solution that can be explored. Namely, the speed is related to both the width of the wave as well as its height. In other words, there's a very clear relationship between the speed and the profile, which is something that Russell also observed in his experiments. The second thing is f is always negative. Okay, so this doesn't seem to match with the experimental observation, except that we need to change send u to minus u if we want to make direct connection with the experiment. So always remember the solutions of the KdV equation here correspond to the physical Russell experiments if you make u go to minus u. So what I want to do now is simply give you a feeling for what these profiles actually look like for various values of c. What I'm going to do is plot this wave at times t equals to 0 with x0 equals to 0, so it's a wave centered at the origin, and then plot the wave at times t equals 12 units later. The initial wave is red, then the final one is blue, and I will do it for several speeds. So we start with c equals to 0.5, you have the following two profiles. If you start with c equals to 1, the wave increases, the width decreases, and the separation increases, which indicates that the speed is greater, which is basically what the parameter means. C equals 1.5, wave increases further, width decreases. And here you can actually see that the width goes like the square root of the speed as well. C equals to 2. You basically, here are the heights increased. C equals to 2.5, and we keep going. Now it's very important to note that only one of these waves at a time can be a solution to the KdV equation. The superposition principle that we have in linear waves simply doesn't work, and you can actually try and show that it doesn't work because of this nonlinear term. So these waves cannot be superimposed on top of each other. What can happen, and in fact does happen, that there's a non-linear version of the superposition thing, which we'll explore when we look at the two-soliton solution. So in the next figure, I'm simply going to, for purposes of keeping the slide, put all these plots on top of each other. Please note that that is not a solution to the KdV equation, just an individual hump like this at one time and then at a later time depicted here can be, but the next picture must never be confused as a solution to the KdV equation. A solitary or a traveling wave solution of this form only has this profile, and there's only one of them. Okay, but just for record purposes, there's the graph of all of them. And just detailing what I've said, for a given C, there's a fixed shape for all time by ansatz. The height and the shape depends on the speed, C only, so it's a one-parameter family of possible profiles. F is always less than or equals to 0 for traveling waves, which is consistent with Russell's experiments. If you let u goes to minus u, the solutions can be shown to be stable, which is important because only stable solutions of PDEs are realized in physics, and this has been proven. Okay. Right, so that's one special case of solution, the traveling waves. The next special case of solution using very similar techniques are going to arise by something I mentioned at the end of lecture 28. Namely that I showed that the equation, the KdV equation here, is invariant under similarity transformation. So what that means, I must just simply remind you again, is simply if you let x rescale x with a linear parameter, you rescale time with a cube of the same parameter, then the solution is rescaled by u over gamma squared. Okay, and we're going to use this similarity transformation to look for solutions. Okay, and what we're going to do, the way we're going to seek those solutions is much the same way to how we found the similarity solution to the heat equation. When we've worked out the Green's function for the heat equation, we're simply going to say, we're seeking solutions where u of x and t is equals to gamma squared, which comes from there, u times gamma x plus gamma cubed t. Basically, we're rescaling the independent variables, and we're going to assume that that holds true for all gamma x and t, even though, and we note that gamma doesn't appear explicitly in the KdV equation. And so that we're going to make the simplifying ansatz by setting, it's not an ansatz, we're simply going to simplify the problem by setting gamma equals to t to the minus 1 over 3. And if we do that, we're going to have to introduce another variable, which becomes then the sort of new independent variable, or the similarity variable in particular, if we call it, and it's going to be x is equals to t to the third. In other words, x is simply going to be equals to this thing, or eta is going to be equals to this thing, where we've replaced gamma by the choice of gamma. So t to the minus 1 over 3. Okay, so we're now seeking solutions of this kind, which basically now depends on one variable, the similarity variable, and it's going to be, we're seeking solutions where g is equals to t to the minus 2 over 3 g of eta. Okay, so much similar to the way we found traveling wave solutions, except that our ansatz is now different. Okay, but we proceed in the same way. We work out the consequences of this ansatz by working out what ut is, and ut is simply the derivative of this prefactor over there times g of eta minus g prime of eta, the prefactor times the derivative of eta with respect to t, okay, which is then just this. Okay, g of x is simply this prefactor times g prime times the derivative of eta with respect to t, and combined with that, the prefactor, we get it's 1 over 2 g prime. Gxx is simply g double prime d eta dx times 1 over t, and g triple x is simply that. Okay, we take this, we substitute it back into this KdV equation, and what we then get is this equation. Okay, this equation, although it looks very similar to the one we've just solved for the traveling wave solution, is actually a much harder equation to solve. Because it doesn't have elementary solutions. In fact, this is a fascinating equation which can be shown to reduce to the Paine-Levy's equation of the second kind. I'm not going to give the reduction. What it basically means is there's another equation that's entirely equivalent to this reduced KdV or self-similar KdV equation that has this form. In other words, you have y, which is actually just a rescaled version of eta, and you have v that has some relation to g. And then you have this. And this equation is known as the Paine-Levy equation of the second kind. And it's a very special type of equation. Usually when you have a first course in ODEs, you have all sorts of techniques for solving them. You learn about the Schumann-Ville problem, and you learn about series expansions for solving the equation, much like we did in the last problem set. And then you stop there. But what happens is that there's one more technique, and actually only one more, basically one more technique that allows you to solve, or that allows you to increase your knowledge about second order ODEs, and this is the Paine-Levy property. So what they basically do is, instead of making an expansion, just a power expansion, they make an expansion, but they say the poles, in other words, they make an expansion where you multiply the expansion by 1 over the independent variable minus a pole that changes in time. And there's a technique, and Paine-Levy looked at all those problems, classified them, and reduced the number of equations that you could get out with a specific property to be about 5, of which this is 1. And then he solved, and then he explored the properties. Okay, so it has only movable singularities or poles, and the reason I am not going to solve it further is that it cannot be expressed in elementary functions. It actually is a new kind of function that solves this equation. And that's proven. A lot of the properties are known and were explored by Paine-Levy because these equations actually occur a lot. So I just want you to know about it and to know that this thing exists, that it goes beyond what's normally taught about second order ODEs. And this is what it looks like. Okay, and this particular equation is actually found very, very often in integrable systems and also in integrable PDEs. Okay, so it's worthwhile knowing about and studying it. And one of the experts in studying the Paine-Levy equation is actually South African. It's Professor Andre Weideman, who stays at Stellenbosch University, or works at Stellenbosch University, and he works out numerical methods of characterizing this equation, which is a topic of current research. And very valuable because it actually explores elementary, or sort of, it's used often when you start working with integral systems. That concludes the first part of this lecture, and during the second part I'll be starting to look at a general method of solving the KdV equation. Thank you very much.